kind of a tree themselves. They're a subtree. Now trees have what we call leaves, and those are all of these guys. So these are what we call leaf nodes. They basically don't have any other branches, because you could picture this as a branch. You're basically from one part of the tree, you're taking yourself to a different part of the tree. These guys here are the leaf nodes, because from themselves they do exist, but they don't have a left and a right. So their left would be null and their right would be null as well. Now you might also hear the term parent. So here, if you're regarding some particular node, this could be a parent to its different children here. So this would be one of its children, and this would be another child over here. So if you're ever talking about a parent-child relationship, we mean the one that's above it, basically. So from the parent, you would go down to the children. Now what's kind of counterintuitive about the relationship is that notice that when I was drawing my class here, so if I had an object here, I had a root and it has a value, a root.val. It also has a root.left, so that's basically its left child. It has a root.right, but what we generally don't have, although you totally could, is the root.parent. This just doesn't exist in most implementations for who knows what reason. LeetCode decided that it's not going to be present, so generally this is the relationship we're given, which means more formally it should be written like this, because as we'll see, trees are actually a subcategory of graphs, and so trees are actually what we call directed graphs. We have a direction. We have from here you can get to over here, but from here a child you can't actually get over to your parent. Again, in some implementations you could have that existing, but in LeetCode generally this is the class you're going to be given. Okay, there's a little bit more terminology here. Particularly, this tree is actually a specific type of trees known as a complete tree, or sometimes called a full tree. And a complete tree means that this level is fully filled out, so is this one, and this one is mostly filled up from left to right here. So basically we don't have this last piece here. If we did have this last piece, so this is some number here, well then this is actually what you call a perfect tree. So it means it's completely filled up here. We have the three levels. We have one thing here, two things here, four things here, and nothing is at the end. So that would be a perfect tree. What we have here is a complete, sometimes called a full tree, which means it's all the way filled up except possibly the end. We're missing something at the right side, and that's totally fine. And this would also be a complete tree as well. This would also be a complete tree. And so with this one, this is a complete tree and it's a perfect tree. But then if you have this here, this is not a perfect tree, but it is complete. Now, something that's kind of interesting about binary trees is that you can actually kind of think about them as an array. So let me kind of move this over here and draw its array representation. So this is the representation that kind of in memory, meaning that if you create objects that have a class, this is how it would look with like one thing pointing to another thing. But in theory, you could kind of have this as just an array, because if you had, and let me just leave the first position blank here, you'll see why in a moment. If you had this one as 1, then 2, then 3, then 4, then 5, then 10. Notice I'm just drawing it in order here. So given some index I, which is going to be 1 here, well then its left child is going to be located at 2 times I, and its right child will be located at 2 times I plus 1. So let's just test that out here. If I is equal to 1, we're saying that its left child would be at 2 times I, which is 2. So that's right, because the parent is 1, its left child is 2. We can see that over here. here. And for its right child here, we can see that it's going to be 2 times I, which is 2 plus 1. So that means its right child is over here, and it is, because for 1 is the parent and 3 is the right child. We have that relationship right there. And that is going to work for any position in the array. The only problem is that if you have something like 4, we would have 2 times I should be your left child, which is located at index 8, except that's outside the array. So if you go outside the array, that just means it's null, meaning we don't have any there. Now this also works if you don't have a complete tree. So if we had something like this tree here, well, this is totally valid. It's just that it doesn't have a right over here. So we lost the 3 and the 10. Well, then if we're talking about the 1, well, then its right child should be at position 3, which is over here. And so if you have a blank here, or you could kind of mark this as, say, a -1, well, that's just a way of saying that it's null, and that's totally correct. So binary trees have an array representation as well, and you'll often see this in LeetCode. LeetCode might actually tell you that this is kind of the input you're given, and it might look like an array, but if they're talking about trees, they're probably talking about a binary tree representation given in its array form. Now, another important quality of binary trees is that they generally have a height. And so the height is basically just the depth here. So including this node here, the root all the way down to the bottom, this would have a height of 3. And you might also see this called maximum depth. So basically this is depth level 1, 2, and 3. So it has a height or maximum depth of 3. Now subtrees also have a height as well, because if you're talking about kind of this guy as the root here, well then he is a tree. It's a subtree of this main tree. And so this tree would have a height as well. So this guy, he would have a height of 2 because he has himself and he also has going over here. And so that means we could kind of define a leaf node as something that has a height of 1 because it just has itself. It has nothing to the left and nothing to the right. And just to be super clear about the height here, if the tree actually looked like this, well, we wouldn't go down to the right side because that is nothing. It's going to be basically the maximum of going from the top to the bottom. So we would ignore that there's nothing to the right, go from the top to the bottom, and we would see this still here has a height of 3. Now in practice, we're generally concerned with some sort of traversal on the tree. So for example, you could do what's called a depth first search, or basically a depth first traversal, where you're going to start at the root because that's what you have access to. And we prioritize depth, which goes this way. So if you go over to 2, the next thing we're going to see is not 3. In a depth first search, we're prioritizing depth. So we're going to keep going down all the way. And generally how you do this is you go down and left all the way first. So we see 1 and then 2 and then 4. And then after we see the 4, well, we're still going to try and go left here, except that's null. So that's nothing. So we'd kind of quickly come back up here and see, okay, after we've seen the 4, well, then we're going to go right. Okay, there's nothing there. Now we're done with the 4. We've visited both itself and its left and its right. We're done with that. And so we're at the 2. Now we need to see its right side, which is going to be the 5. So we see the 5. Okay, cool. We see its left, which is nothing. Its right, which is nothing. We come come back up here, and then we're done with the 2, so we come back up here. With the 1, we still haven't visited its right side, so we will see the 3 next, and then we are going to see the 10. So that is going to be the order of our traversal. This would kind of return back up here, return back up here, and then we'd be done our search. Now for depth first search, there's basically 3 different ones that you might do, and they're all very similar, but just a slightly different order of processing. So there's going to be pre-order traversal, there's also in-order traversal, and there's also called post-order traversal. And what this means is basically the order in which you process the node itself and its left and its right. Pre-order traversal basically means that you first consider the node you're currently looking at. So if you're looking at this guy here, it means you process it, which just think about printing. So basically you'd print the value of 1. So we process process the node itself first, then you process its left thing, and then you process its right side. Okay, so you first do the node, then the left, then the right. We actually just did a pre-order traversal. So we'd visit the root and we immediately process. Let's see the 5. Okay, its left has nothing, and then we process itself, which is going to be 5. Its right has nothing. We come back up. We come back up. Now the 1 says that, okay, we've processed its left. We're ready to process the current node, which is the 1. And so now we actually process the 1. Even though it's the first thing we visited, we still started here. We only processed it, aka printed it at this point. Okay, so now we've processed the current node. We then need to go right. So we do that for this guy here. Before we process it, we need to go left. So we are going to go left over here. Okay, now we can process the 10. We return back here. Okay, the 3 has done its left. Now it's ready to process itself. So we process the 3 itself. We do the right, which is nothing there. We return back. And then finally here for this 1, we've done all of its left, itself, and its right. So that has done the traversal. So this is what we would get in an in-order traversal. Okay, now let's do a post-order traversal. So what that means is the first thing you do is go left. And the second thing that you do is go right. And then after you've processed your left and your right side, then what you're going to do is yourself, your current node. So what that's going to be is you visit 1, but we go left. We visit 2, but we go left. We visit 4, we're ready to process itself. So again, the first thing you're going to see here is the 4. Hey guys, Greg here. Let's talk about time and space complexity as well as big O notation. Now when we talk about these things, we generally have some sort of input. So we'll say we have an array of just the first. Hey guys, Greg here. Let's talk about a popular algorithm known as recursion. Now to illustrate this idea, let's talk about the Fibonacci number problem. So the Fibonacci numbers are a sequence generally starting at 0 and 1, and then the next number is recursively defined as the sum of the previous two values. So the next number would be 0 plus 1, which is 1. This would be 1 plus 1, which is 2. 2 plus 1, which is 3. We'd get 5, 8, 13, and so on. That sequence is actually infinite. That can keep going. So formally, you would define this with a function saying something like f at 0 is equal to 0. That's one base case. F at 1 is equal to 1. That's another base case. But more generally, for any n that's bigger than 1, we would have that f at n is equal to the sum of the previous two, which is f at n minus 1 plus f at n minus 2. So this is the formal way of saying your base case, f at 0 is 0. You could think about this basically as an index here. F at 0 is 0, and f at 1 is 1. And then for any n that's bigger than 1 here, so for 2, 3, 4, 5, 6, and so on, you'd have that f at n is equal to f at n minus 1 plus f at n minus 2. And if you were to write a actual function out of this, we'll just use Python because it's basically pseudocode. We'd have defined f at some value of n here. Well, you'd have your base cases. So if n is equal to 0, then the base case just says we would return the value of 0. So otherwise, if n is equal to 1, well, that's your other base case. So in that case, you would want to just return 1. But more generally, if it's not one of the two base cases, if it's not one of these two, then it's actually recursive, which means you'd have to call the function that you're using, the function f, within this function itself. So basically, otherwise, you'd have to return the value of f at n minus 1 plus f at n minus 2. Okay, this is the recursive part right here. From within this function called f, you are actually calling that same function f. That is what it means to be a recursive function. You're calling yourself. Okay, so let's see an example of this. So basically, if you called something like f at 5, if you wanted to know what f at 5 is, well, it's going to set 5 over here. Okay, well, and it's not 0, it's not 1. And so we would actually return the result of f at n minus 1 plus f at n minus 2. So what it would need is f at n minus 1, which is going to be f at 4, and it's also going to need f at 3, so that's f at 5 minus 2. And so the result of this is actually going to be the addition of these two calls. Okay, but this is recursive, and so f at 4 here, well, that itself is going to actually need f at 3, and it's also going to need f at 2, and this is still recursive here, so let me just move it up a bit. F at 3 is going to need f at 2, and it's also going to need f at 1, and f at 2 2, well, that would need f at 1, and it would need f at 0. F at 2 is going to need f at 1 and f at 0. And let's just copy and paste this stuff here, because f of 3 over here, well, it's going to need the same stuff over here. So f at 3 over here also needs all of that information. And so to work out this information here, well, at the bottom, we know that these base cases are actually numbers. And so these are basically leaves in this tree here. It's kind of like a recursive tree. And so the leaves are numbers. F at 0, that is a number, and so that is 0. F at 1, that is a number, which is 1. And now we know that f at 2 is 1 plus 0. And so we can replace f at 2 with its value of 1. F at 1, again, these are all going to be replaced by 1s. Those are 1s. This one is also a 1, and so is that. Okay, these ones are going to be 0s. And you can see we're basically doing duplicate information here. We already learned earlier that f at 2 was 1, but we're going to replace it again over here with this is going to be 1, and this is going to be 1. So the f at 3s, they are all going to be 2s. So this is going to be a 2, and this is also going to be a 2. Now the f at 4 will be replaced by 3, so this is 3. And finally, we know that f at 5, that is going to be a value of 5. And you can actually see that over here. We already computed that earlier. Now, when a function is recursive, you'll often hear this term called a call stack. So it is a stack because it literally is a stack data structure. This is why recursion comes after the stack sections, because it uses a recursive call stack. And by call, we mean that's basically short for function call stack. So this is our function, and we can see we're calling it many times here. These are calls of the function. And so when you're calling the function within the function itself, it is recursive, and it's going to generate what we call a function call stack, or sometimes called a recursive call stack. So let's say we wanted to compute f at 4 here. Well, I'm actually going to put that on the bottom because it's a call stack. We could think about it as building up. So what the call stack would be for this, it's going to look like this. So the call of f at 4, that's again why it's called call stack, because for this function call of f at 4, well, it stores certain information. It basically says there's this local variable n, which is equal to 4, because throughout this call of the function, n has a value of 4. And function calls also have memory addresses. They basically have what we'd call a return address. It's just going to be like some hex code, so 0x, and then a bunch of information here. We'll just call it 0x123. And so for simplicity, let me just kind of think about this as address A here. So what f at 4 does, well, it says, okay, n is equal to 4 throughout this function call. And so the first thing it needs to know is the value of this, which is going to be f at n-1, which will be f at 3. So it immediately calls this function here, and that's why it generates the call stack. So f at 4, it first needs to know the information for f at 3. And so now we're in a new call of the function here. Throughout this call, it is n equal to 3. And so here it stores information. Here n is equal to 3. And it also has an address to return to. I'll just write address B, for example, here. It's some hex code. Okay, so f at 3, well, it would need to know f at 2 plus f at 1. And so the first thing it does is it's going to go over into f at 2. So we'd build this up again. So we'd say, okay, well, we'd have a spot for f at 2. And so throughout here, n is equal to 2. And we'd store our return address. So we'll just call that address C, for example. Okay, so over here, we'd be concerned with n is equal to 2. And so f at 2 would need f at 1 plus f at 0. So the first thing it needs is f at 1. So it's going to go over here. And so we have f at 1 over here. Okay, so f at 1 is very interesting because we store here that n is equal to 1. And we'd have a return address of D. And what's interesting about f at 1 here is that it is not going to kind of build up the stack here. It is at what we call a base case. And recursive functions, they need some sort of base cases here, because if you didn't have them, they'd basically just call forever. They would just infinitely call the function and you would never return. So here we've hit a base case, which is f at 1. And so here at this function call level, we just return 1. Return? What does that really mean? Okay, we return to where we came from. Well, we came from f at 2. So we're basically telling, hey, f at 2, you called me, you called f at 1. Well, my value, I'm going to return that to you, is the value of 1. So basically we would go back to f at 2 here, and it would kind of remember here, it would say, okay, we called this guy here, we called f at 1, and so his value is actually equal to 1. And so we'd also need to call f at n minus 2. So he would want to know what the value of f at 0 is. Currently it's just a question mark. So we would go and get f at 0, and so f at 0. In this context, we have n is equal to 0. And again, you would have some address, but I'm going to stop writing it. It's going to be some address. We'll call it e. And so again, f at 0 is a base case, so he's not going to build this up any further. And so he's going to return to f at 2 via this memory address here. So that's why we need the memory address, because f at 0, we need to know where to return to. We return to where we called it, which in this case is address C associated with f at 2. So we return our value of 0 over to this memory address, or basically telling f at 2 here that its value of f at 0, that function call, has a value of 0. Okay, it now knows that f at 1 is 1 and f at 0 is 0. So it knows the value of both of these two calls. And so now f at 2 is able to return the value, which is f at 1 plus f at 0, and its value is going to be 1, which is the sum of those two things. Okay, so f at 2 is 1. It's going to return to the thing that called it, which is going to be f at 3, which is located at memory address B. So it basically says, okay, hey, f at 3 here, well, your value of f at 2, that is going to be a result of 1, but then f at 3 also needs to know the value of f at 1, and so it's going to then put that on the call stack. So f at 1, I'm going to do this a little bit faster, and so it would basically return here that its value is a base case, which is just going to be the value of 1. So that's how we know that f at 3 is 2. We return this information back to where we called it. So f at 4 knows that its value of f at 3 is a value of 2, but f at 4 also needs to know the value of f at 2, and so we kind of build this call stack back up here. F at 2, well, f at 2 is not a base case, and so it needs to know the value of f at 1, which is currently a question mark, f at 0, which is currently a question mark, and so we could draw that for f at 1 here. That's going to quickly kind of return here and say that the value of f at 1, that is a base case of 1, f at 0, that would tell us that it has a value of 0, and again, f at 2 would basically return the sum of these two values over to this call here, and so it would tell it that f at 2, this value is going to be just 1. So now f at 4 actually has the total value here of f at 3 plus f at 2, which is going to just be 3. So f at 4 has a value of 3. Okay, so that's the recursive call stack and the fundamental idea of recursion. So just to really illustrate what would happen here, if you called something like f at 4, well, it's firstly going to do this before it even thinks about this idea. So the placement of this actually has a huge effect on the way that the computer is going to run this. It first is going to see f at n minus 1 before worrying about f at n minus 2. So f at 4 is actually first going to think about f at 3, and then it's a recursive call. So f at 3 thinks about it the same way. This guy needs to know what f at 2 is first. So he goes and gets f at 2, and f at 2 is going to first think about f at 1. Now we hit a base case, and so f at 2 can kind of remember that f at 1 has a value of 1. Okay, f at 2 also is going to need f at 0, which we'd return back and say that's a value of 0. F at 2 would then basically return to f at 3 that it has a value of 1. Now f at 3 can think about f at 1, and so f at 1 is going to be a base case of just 1. Okay, f at 3 is now going to return to f at 4. Then it has a value of 3. So what happens is you can see there's one thing at this level, there's two things at this level, 4 at this level, and if we picked a high higher value here, this actually would have had at most 8 things here and then 16, and you basically get a doubling effect. So what's basically happening here is that there is 2 to the 0 things at this level, 2 to the 1 here, 2 to the 2 here, and 2 to the 3 here, and so on. So you're getting a doubling effect starting at n, and that's going to work itself all the way down to 0. So there's approximately n things. or n plus 1 things there. So basically in the bottom level, you're going to have roughly 2 to the n things. So you can think about this as a time complexity of big O of 2 to the n due to the doubling effect. So the doubling effect happens because at any f at n, you basically need to sprout off into 2 different pieces here. So your 2 is coming up because you basically have 2 different options here, and
The setup of the problem is as follows. You have 3 rods. One of the rods has some number of discs of varying sizes placed on it, with the largest disc at the bottom and the smallest disc at the top. Your goal is to move these discs one at a time to a particular destination rod in the same configuration as the start. Before you get ahead of yourself and declare this problem trivial, there is one important catch. At any point in the process of moving discs, you are not allowed to move a larger disc on top of a smaller disc. This rule is what makes this problem significantly more challenging to solve. In this video, we will dive into the Towers of Hanoi problem in 3 distinct phases. First, we'll approach it from the perspective of a puzzle, where we'll try to come up with a strategy for various configurations. Then we'll transfer the strategy into a recursive program to solve this problem for any number of disks. In this section, I'll also show you some helpful tricks to solve challenging recursive problems like this one. And lastly, we'll deconstruct the recursion to understand what's really going on underneath the hood with some nifty animations that I'm pretty sure you won't want to miss. So make sure you stick to the end of the video. Alright, let's get started. Let's focus first on 3 disks, since the solutions to the 1 disk and 2 disk setups aren't too interesting for analysis purposes. I highly recommend pausing the video and taking a second on your own to see if you can find the set of moves to get these 3 disks to the rightmost rod. Our goal is to come up with a general strategy for solving this problem. If you're like me, your first go-to strategy in any type of puzzle is random guessing. And honestly, there's no shame in that. Random guessing is the oldest strategy in the books. So if I'm looking at this problem, the first thing I might try is to move the smallest disk to the middle rod. And then the next move is basically forced from there. I would move the green disk to the rightmost rod, since I can't move it to the second rod because that would violate the rules. After that, the next move that makes the most sense is to try and move the smallest disk to the rightmost rod. And at this point, after I've finished completely destroying the order of this problem with 3 random moves, I think it might be a good idea to evaluate what I've done so far. Well, unfortunately, it's not looking too good. It looks like we are a little bit stuck because what we really want is the bottom disk below the disks that we currently have on the 3rd rod. What we just did by random guessing seems to be pretty counterproductive to that point, so at this point in the problem, I might decide, okay, I might just want to start over and reevaluate. But from this random guessing experience, we've learned one important fact. We need to first think about moving the largest disk from the first rod to the destination rod. And if we take this idea one step further, before we can even think about doing that, we're going to have to deal with the top two disks. And we have to deal with them in a careful manner so we can eventually move the largest disk to the destination rod. This means our only option is that we have to find some way to move the top two disks to the second rod. Okay, so now that we split our problem into more reasonable subtasks, let's solve them one by one. To move the top two disks to rod 2, we first move the smallest disk to rod 3, after which we move the middle disk to rod 2 and finish up the subtask by moving the smallest disk to rod 2. And now we are free to move the largest disk to rod 3. Alright, so what's next? Well, from here the solution is actually pretty clear. We need to move the top two disks from the second rod to the third rod now, and to achieve this, we move the smallest disk from the second rod to the first rod to get it out of the way. We then move the middle disk from the second rod to the third rod, followed by the final step of moving the smallest disk to the destination rod. And there you go, we've just solved Towers of Hanoi for 3 disks. Here's a quick recap of what we did. We first found a way to move the top two disks to the second rod, allowing us to then move this largest disk to the destination rod, and after this, we finished off by moving the top two disks from the middle rod to the destination rod. Okay, so now let's go one step further and see if we can solve this for the n equals 4 case by utilizing a similar strategy to what we've just developed. Before I go through the steps to solve this, take a second to pause the video and see if you can come up with the steps on your own. Applying the general strategy to this new problem, we want to now move the top 3 disks from rod 1 to rod 2. How do we do this? Well, one interesting thing about solving this problem is that it's basically like ignoring the largest disk even exists and solving a general 3-disk Towers of Hanoi problem, where now our destination is the middle rod. Make sure you take a second to understand the mapping that we just did. And looking at this simpler problem, we know how to solve it now, right? We basically solved a version of it earlier. To solve this subproblem, we move the top 2 disks to the third rod. We achieve this by moving the top disk to the second rod, the middle disk to the third rod, and finish off by moving the top disk from the second rod to the third rod. This now makes way for the largest disk moving into the desired position. And now to finish off this subproblem, we once again move the top 2 disks, but this time from the third rod to the second rod. This subtask breaks down into moving the top disk to the first rod, followed by moving the second disk to the second rod, and ending with moving the top disk from rod 1 to rod 2. Notice the logic that we used here was essentially the same as what we did earlier, and this is something that will be immensely important going forward. In a sense, this is where the recursion of this problem really originates. Going back to the 4-disk problem, we now move the largest disk from the first rod to the destination rod. And now, following our earlier strategy, we now move the top 3 disks from the second rod to the destination rod. And the pattern once again shows up. This is essentially the same 3-disk problem we've solved many times now. We move the top 2 disks from the middle rod to the first rod, and to do this, we move the top disk from the second rod to the third rod. We then move the second disk from rod number 2 to rod number 1. And we finish the subtask by moving the top disk to the first rod. We then move the third disk from the second rod to the destination rod, and our final subtask is to move the top 2 disks from rod 1 to rod 3. Once again, we know how to do this. We move the first disk from rod 1 to rod 2, move the second disk to the destination rod, and finish off the whole problem by moving our top disk to the destination rod. And that's the sequence of steps for Towers of Hanoi with 4 disks. I know that was a lot, so let's do a quick overview of what we just did. We first moved the top 3 statement. We want to write a function Hanoi that's an example of an input and output so that we understand the top disk from rod A to rod B. Okay, so how do we get started on solving? Throughout my years of learning computer science, knock down the first domino. You want to show that the nth domino will eventually be knocked down. How do you do this? Well, you know that if you just have one domino, it's obviously going to work out because you can just knock it down. This is an analogy to step 1. From here, what you can do is just assume at some point the n-1th domino will eventually fall. This is the analogy to step 2. And now, to guarantee the nth domino will fall, we have to put this domino just close enough to the n-1th domino so that when that domino falls, the nth domino will respectively fall. This is the analogy to step 3. And once we do that, all the dominoes fall. I want to emphasize here that all 3 steps are equally necessary for this to work out. If we don't get the base case right, that means the first domino never falls. If we don't make the assumption that f called on n-1 works, that's similar to the situation where the n-1 domino never actually falls, in which case there's no way that the nth domino is going to fall. And lastly, if we don't properly define the relationship between f of n and f of n-1, that's basically like putting the nth domino too far away from the n-1 domino, so in that case the nth domino also never falls. It's by moving the domino close enough to the n-1 domino that the nth domino falls. So let's now apply these 3 steps to solving towers of Norrie. Starting with step 1, we want to show how we appropriately handle the base case for this problem when n is equal to 1. That's how subproblems work. Now, with that assumption solved, and third rod lead to moving the last disk these steps succeed. And for completeness, he is a fully divisible disk to move from 1 to 3. Here's a visual example of what this call is trying to achieve. And this recursive call step involves the final recursive call on one disk moving from the first rod to the third rod,